Hello, friends. Today we're going to practice doing calculations to determine how much weight a boat can hold. As you can see, I have the worksheet here that we've done in class on Tuesday, and I'm just going to go through it today. So this example is just a rectangular boat of 20 by 40 by 20. A good practice is to draw the boat. I'll draw it in red so the water will be blue. It's typical, right? This is not as much to scale as I wanted because it's 20 by 40 by 20. So really I need this to be a little taller if I wanted this to be accurate. So if this is 20 wide by 40 deep by 20 high. Let me draw this a little better. So 20 wide by 40 deep, and you do the parallelogram thing by 20 high. So this will be a square. There we go. Please take these numbers literally. Obviously, when you do your boats, you're going to draw your boats very accurately in a schematic. So this is my rough schematic of a rectangular boat. This is going to be mostly hollow, but it has a mass of 1 kilogram just in its materials itself. And of course, draw an accurate to scale forest diagram. Here's accurate to scale. We have MG pointing down and FB pointing up. So which wins? Well, the whole point is that when you're on the surface of a fluid, only part is submerged. So this now becomes, right? My water is three-dimensional here, right? Right? This now becomes the only important part of the boat that matters. This V sub is the only part that the water is squeezing. And remember, the water squeezes and ultimately produces an upward force of buoyancy. So squeezing inward pushes it up. That's buoyancy, and it only depends on V submerged. So even in the formula, we have FB is density of fluid times volume submerged times gravity. And so we can figure out the submerged volume. What volume is submerged? How? When we say which wins, it's floating. It's not going up. It's not going down. It's just sitting there. So if it's just sitting there, what's the net force? It's zero. That's the key to a floating object. When I say something's floating, not rising, not falling, but floating, it's not moving, right? V is zero, F net is zero, velocity is zero, acceleration is zero. It's all just sitting there. I think it's more important that it's not accelerating versus not moving, but clearly it's not doing either. It's not doing anything. It's just chilling, right? So what we can say, of course, is that since F net is zero, you can do up minus down equals zero. F net equals zero. So I'm just plugging F net is FB minus MG. I'll call that negative, call that positive. But really, it just means that they cancel. FB equals MG. Of course, up equals down. So we have rho fluid V sub G. This is rho fluid equals mg. This cancels. And we notice we have the mass of the boat equaling the mass of the displaced fluid. If you can figure out that, you're on it. This is the mass. See this volume that's displaced? That's the mass of the displaced fluid, which means the buoyancy force is the weight of the displaced fluid. That's called Archimedes' principle. And that's like a ding, 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 like extra special conceptual realization where you realize that's really what's going on. So I'm going to write the answer right here. I'll keep it in red. So we have that cancel, that cancel. So we have the mass of the displaced fluid, which is 1,000 times its volume, equaling 1 kilogram. So V sub is 0.001 cubic meters. Remember, we're in cubic meters here, which of course is 1 liter. So we have 1 liter submerged. Now, the smart shortcut is that we have 1 kilogram pushing down times G, of course, weight. And therefore, we have 1 kilogram pushing up times G. And 1 kilogram of water, definition, is 1 liter. If you see that shortcut, you have done the amazing conceptual and mathematical work, which was really the entire point of this project, is to have that realization. Although really the point is to go through the nitty-gritty forces, but really that coming out the other side and realizing 1 kilogram displaces 1 liter, boom, of water, of course. 1 kilogram displaces 1 liter of water. So if I'm pushing down with 1 kilogram of weight of the boat, it's going to push back with 1 kilogram. Sorry, one equivalent of 1 kilogram. I know it's mass, but times G, it's going to push up with 1 kilogram of water. Boom! It's 1 liter. Ah, that's the realization. I hope that makes sense. Anyway, please show that the math gets you there, but that's the shortcut. It's pretty cool. And I said down here, have you found the shortcut and deeper connection yet? We're going to have that in class. So what you can do, so I'm going to erase this. Pause the video if you need to. Clear. And if you add 2 kilograms, right? I'm going to do this one kind of quickly now. You can just say, okay, now M total equals 3 kilograms and then repeat. And clearly it's going to sit deeper now in the water, right? It's going to sit deeper. Not that deep though, because if I displace 3 kilograms, that's going to be 3 liters of H2O. But the entire volume is going to be 20 times 40 times 20, which is 16,000. The comma is there. 16,000 cubic centimeters, which sounds like a lot, but remember I divide by 1,000, that's 16 liters or 0.016 cubic meters. I like this one because it makes sense to me. I'm displacing 3 liters of H2O total. The extra volume for 2 kilograms is going to be 2 liters more displaced. You can repeat the FB MG analysis to get there, but really the shortcut is if you're pushing down with 2 kilograms, it's going to push up with 2 kilograms equivalent of weight, which is 2 liters more displaced water. Boom. So if I'm out of 16, so the first one, question one, was 1 liter out of 16 liters is 1/16 of the boat. That's one, and there's the 1/6 of boat submerged. 1/16 of the boat is submerged. Here, 3/16 of boat submerged. That's the answer. So you can repeat the analysis. You should get 3 liters. 2 liters more displaced is the shortcut. That's the deeper connection, Archimedes principle. Boom. What fraction of the total is submerged at 3/16? Draw an accurate drawing of 3/16 submerged. I'm not going to do that, but I'll trust that you guys can draw in 3 dimensions and draw 3/16 submerged. I think I asked like what height is submerged. So if you want to do that, be like, okay, it's just the height was 20. So whatever 3/16 of 20 is, I can probably do that in my head. That's 5/4. 5/4. That's 20 divided by 16 is 5/4. 5/4 is 1.25 times 3 is 3.75 centimeters is submerged. Which is going to be important because as you add weight to your boat, that's gonna displace more volume, but the area stays constant. So really, you're just the fraction submerged is going to be the fraction of the height. So if it's half the height, you're going to say, well, is that going to start leaking because now there's a hole there or something like that? So that's what you're going to want to think about. So that's awesome. Now for the most important part, which is the last one, which is what is the maximum amount before this boat sinks? So how do you do this? Well, how you do maximum amount is pretty easy. You just like, well, if I'm going to keep adding mass, it's going to go deeper and deeper. It's going to go deeper and deeper. Why? Because there's more weight pushing down. And if there's more weight pushing down, I need more buoyancy force pushing up for them to cancel. So if this increases, this has to increase. But remember, this is rho fluid V sub G. So the fluid isn't going to get more dense. Gravity isn't going to get more stronger. So that means V sub must increase to provide more buoyancy. That's the reason why, right? And it also makes sense. Clearly, if you increase this force, right, by adding more weight, it's going to push the boat deeper, which is going to increase this force until they match, and then it's equilibrium again. So at what point does it just sink? Well, clearly that's when it's almost entirely submerged. Like the point before, just before water starts creeping in. You do not want to be in a boat that is almost all the way sunk, right? So the point of max cargo, and this is obviously the boat's mass included. So this is total mass, and then we'll subtract boat mass to get cargo. Cargo is what's placed inside. But we'll solve for M total, right? So this is M total. So we have FB equals M total times G. But FB is now where V sub, here's the trick. Max cargo is when V submerged is V total because it's all submerged. So this was 16 liters. So I have rho fluid, V submerged, which is V total. This is only for the max cargo calculation equals M total G. G cancels, and I get the mass of the displaced fluid is the mass that's total. The mass of displaced fluid, of course, is 16 liters, which is 16 kilograms. So I get max cargo equals 16 kilograms. That's the shortcut. If that made sense to you, that's great. If it didn't, you follow the force algebra. The algebra is really simple. You just have to think about what is V sub. It's V total. So I have 1,000, and please don't plug in 16 here. It's 0.016 cubic meters equals M total, but of course that will give you 16 kilograms. Boom. That's it. Max cargo is 16 kilograms because it's 16 liters displaced. And that is the greatest shortcut ever. It's so good. If you can connect that, you're like right on so much. So cargo, I guess the cargo plus boat. Careful. Don't forget that the boat is included in that. A lot of people tend to forget that the boat is included in that. Is 16. So cargo would be 15 kilograms because the boat is 1 kilogram. And total, therefore, total is 16 kilograms that it can hold. Boom. Because the water doesn't care what part is boat and what part is like mass inside boat. The water just feels weight pushing against it. And so it pushes back up to equalize it. Boom. That's it. That's what we got. I hope that made sense. You're going to build boats. They're going to be glorious. You got to think about what happens as you add weight, and that the weight pushing, sorry, the force pushing up of buoyancy is equal to the weight of the displaced fluid. So the mass of the water that displaced cancels the mass of your boat plus cargo. That's it. See you guys in class.